have any question?
So far, so good.
So far, so good. Okay, good. Okay. Um, as you know, this is week number 2, and we try to discuss about instrument types and performance characteristic, particularly in terms of static characteristic. And this is the content of this week lecture or topic. We try to have a brief review on instrument types. Maybe you can um, get the details information in chapter 2 of the reference that I posted in e-learning. And also we try to get into the static characteristic of the instrument. This is types of instrument. We have active, passive instruments. We have null type, deflection type, analog, digital. Maybe this is quite familiar to you guys. We have analog multimeter, digital multimeter, something like that. Indicating instrument to indicate our measurement, and also smart and non-smart instrument. Okay, smart means something like it can process the measurement by itself. For non-smart instrument, maybe you need some other tools to process your measurement. Okay, what is passive and active instrument? Basically, in general, active means that we need external power source. And for passive instrument, we don't need that one. We don't need external power source in order for us to make the measurement. So if you look at the left hand side, basically it's clearly said here, it's a passive pressure gauge. What we try to measure here, we try to measure pressure, and the way it operates, or the work operation of this instrument is that the pressure of fluid is translated into movement of point against a scale. Okay, so if you look at here, we just need a mechanical devices in order for us to make the instrument to make the measurement, and we don't need any external source for that particular instrument. And on the other hand, if you look at your right hand side, we have petrol tank level indicator. So for this one, we have a float type. Okay, float type petrol tank indicator. And if you look at the farthest right hand side over here, we have power source. Means that this device, it's what we try to measure here is we try to measure the tank level, and the tank level measurement needs a power source. So we can say this kind of instrument is considered as an active instrument. Okay, what is the issues with respect to active and passive instrument? If you look at here, we have a resolution of the instrument itself. First, if you look at passive, it is adjustable. You need to adjust the pointer you can adjust the pointer. If you make the pointer longer, means that the reading should be can be a bit different compared to shorter pointer. And it means that here it says make the pointer longer through a longer arc. So we have a longer arc if we have a long pointer, and we have a shorter arc if we have a short pointer. And the problem here is that um, the design itself is limited to its physical setup. So that is for passive. On the other hand, for active, also we can adjust the reading, the resolution of the instrument. And the advantage here is that we have a greater control of the resolution, equipment resolution, because it's an active instrument. Easily we can control it by adjusting values of maybe resistors, maybe the power supplies to it. And also another issue is that it depends on heat effect and safety. So since we have external source connected to our instrument, of course, it will produce heat and as well as safety issue concern or safety concern. Another issue is on the cost. So since we don't have any complex construction in our instrument design, so we can say that for passive it's cheap, and for active it's a bit expensive due of our design, instrument design. Okay, this is a null type and a deflection type. So, okay, can you tell me, is this an active or passive instrument? Can anyone tell me? Silence is gold.
Active.
What? Active? Passive? Oh, someone type over here in our chat room. It's passive. Ma Atira also say passive code. Not sure. Okay, but looking at the design itself, we don't have any what do you call it, external sources in our instrument, or the setup of our instrument. So we can say that this is a passive instrument, and passive instrument also very general. It have null type and also deflection type. So at your left hand side is considered as a null type instrument, and at your left hand side, right hand side is the deflection type. Deflection is very clear here. The pointer over here is deflected based on the fluid and also fluid content inside the instrument. If you look at the null type over here, if you try to the operation, it says here that weight are added on top until the piston reaches a datum level. Datum level means the reference mark over here, also known as the null point. Pressure measurement is made in terms of value of weight needed to reach this null position. So this is considered a null type, and we try to add weight on top of the piston, and once it reach the reference mark, so that is the value of the pressure that we are measuring. I think at the right hand side is very clear. It's a deflection type instrument, since the pointer deflected as the fluid changes and the position of piston changes as well. All right, these are issues in null type and deflection type. First issue is calibration. If you see here, null type is very easy in terms of calibration. When we try to calibrate the instrument, we just need to calibrate the weight, make sure the weight is according to the standards. And for deflection type, it's a bit difficult, but it's still manageable. but a bit difficult compared to null type because we have spring. So spring, you need to make sure the spring is properly calibrated. If it's not functioning well, you need to remove the spring in your instrument. Okay, another one is about accuracy. If you look at the null type instrument, it's more accurate compared to deflection type. This is because of the operation of how do we measure the instrument that we try to measure. Sorry, the measuring that we try to measure. And of course, deflection type is where we can say that it's less accurate compared to null type, but be careful with the calibration of the weight. Again, if the weight is not properly calibrated, for example, if you try to have a weight of 1 kilogram and suddenly the weight, I don't know how the weight change, but if the weight is not exactly 1 kilogram, means that it's never gonna give you the correct or the accurate measurement of the pressure. So, but I think the effect is lesser compared to deflection type, because spring over the time maybe it will degrade its elasticity characteristic. So for the weight, I think the value of 1 kilogram will be the same over the time. Maybe in some case the weight changes, but it's the spring is more sensitive in terms of out of calibration. And in terms of usage, of course, if you have a null type instrument, it's very inconvenient because you need to add weight and then put it back and try again another weight in order for you to reach that null position point. However, for a deflection, it's very easy. Just put your materials on top of the instrument, or whatever, maybe on top, maybe any platform to measure your items, and you can simply get the reading of based on the pointing scale. Another one is analog and digital instrument. Okay, this one is also very clear. At the left hand side is considered as analog because we have a pointer over there pointing at the scale, and for the right hand side we have digital instrument because we have a counter over here. It will count this is a revolution counter. It will count how many revolution based on the revolution of this cam. Very straightforward, these two. All right, issues. Output variation, analog and digital. For analog, consider a continuous one, and for digital, consider a discrete. We have infinite values for analog. On the other hand, for digital, we have finite values. And also, we have a smooth continuous motion based on the pointer move. However, for digital, we have a discrete kind of, I think, changes, value changes given by the counter, the counted value of our analog to digital counter. In terms of disadvantages, for analog, we have the number of different positions that the eye can discriminate. So this is related to parallax error. So if you try to read the analog pointer, make sure it is 90 degrees in a proper eye angle. If you look in different angle, maybe you can get a a different error, different values over there, maybe plus minus 1 degree or plus minus 1 volt, something like that. And in terms of digital equipment or digital instrument, the disadvantage is that it is expensive, of course. And also, I think that the second point, accuracy of control depend on the speed of controlling computer. This is not an issue nowadays, because we know that the speed of computer is sufficient at nowadays. In today's technology, but previously this is quite an issue, because we need a suitable speed of computer in order to get accurate value of the measurement. Indicating instrument, signal type instrument, single type output, and smart instrument. So this is the example of indicating signal type and also smart instrument, the definition of it, how do we apply, and as well as the drawback. Okay, for indicating instrument, we have a null type and also passive instrument. The output might be analog, might be digital. Example, we can see previously, we have a few examples of this indicating instrument. And the drawback here is that human intervention to read and record a measurement. So if you try to read a value, make sure your position, the environment itself, it's suitable. To avoid any errors. For example, parallel errors. It means in terms of try to reading in different angle. Okay, for signal type output, we have the output type is electrical voltage, current, optical signal, pneumatic signals, and the signal type output widely used in automatic control system. And finally, for smart instrument, the definition here is that this instrument which incorporate with microprocessor. So that's why it is called a smart instrument. And normally, the typical application of the smart instrument, maybe you can find it in a hospital where it's used for healthcare, and also maybe you can find it in in industries. For example, in oil and gas industry, we have a lot of smart instrument to measure the pressure and so on. All right, now we get into our main content of this week. What is static characteristic of instrument? So here I've listed 10 static characteristic. We try to have a look one by one. First one is accuracy and inaccuracy of i.e. the measurement uncertainty, precision, repeatability, reproducibility, and also we will look at what does it mean by tolerance, range of span, linearity, sensitivity of measurement, threshold, disturbance, sensitivity to disturbance, hysteresis effect, as well as dead space. So this is the thing that we try to have a look one by one in this lecture. All right, what does it mean by accuracy and inaccuracy? Or in other words, is measurement uncertainty. Here, the definition of accuracy, a measure of how close the output reading of instrument to the correct value. And on the other hand, inaccuracy, the extent to which reading might be wrong. often quoted as a percentage of the full scale reading of an instrument. Okay, if you look at the text that available in this slide, um, you might see that what is full scale reading. Okay, maybe you would like to ask about that. So here I give you an example. Okay, a pressure gauge with measurement range of 0 to 10 bar has a quoted inaccuracy of plus minus 1% full scale reading. Okay, this is full scales mean that if you have uh, here the specification of the pressure gauge is the range of 0 to 10 bar, so the full scale is 10 bar. Okay. Okay, the question here, what is the maximum measurement error expected for this instrument? And the second one is that what is the likely measurement error expressed as a percentage of output reading if this pressure gauge is measuring a pressure of 1 bar? Okay, 1% of full scale reading means that it is 1% of this 10 bar. If you try to answer question number 1, what is the maximum measurement error expected for this instrument? So it is referring to the full scale um, um, full scale range over here, and also the error of full scale reading. So the first question, the solution of first question is that the maximum error expected in any measurement reading is 1% of the full scale reading. So in this case, which is 10 bar for this particular instrument, hence the maximum likely error is 1% times 10 bar. So this is the value of your full scale reading inaccuracy or full scale reading error, 0.1 bar. And to answer question number B, what is likely measurement error expressed as percentage of the output reading if the pressure gauge is measuring pressure of 1 bar? So the pressure gauge now is measuring a pressure of 1 bar. So now here we have the maximum measurement error is a constant value related to the full scale reading of the instrument, irrespective of the magnitude of the quantity that in instrument is actually measuring. So in this case, as worked out earlier, the magnitude error is 0.1 bar. Thus, measuring pressure 1 bar, the maximum possible error is of 0.1 bar is 10% of the measurement value. Okay, maybe you were wondering how this 10% come across. Maybe I need to use my pen over here. Yes, Zaidi, you are raising your hand. Okay. Now. All right, this is our full scale error, plus minus. Let's say we take a minus of this full scale error. To answer question number B, or to question B, it says here that we have a 10% of measurement value. How this 10% come across? So now we have our measurement is 1 bar minus 0.1 is our error over here, full scale error, and we have a measurement of 0.9, and 0.9. Okay, maybe you have other methods to calculate this 10%. Maybe you can also use this method as well. 0.1. 1.1. So the norm to calculate the percentage over here, what you try to do is you take these these values. For example, if I take this value, I have 0.9 divided by 1 times 100% is what? 0.9 times 100 is 90%. 90% of our nominal value of 100%. So for this one is 1.1 divided by 1 times 100. So in this case, we have 110%. So the difference over here, you see, for if you use this calculation, the difference here is 10% with respect to the nominal 100%, as well as this value is 10% compared to the nominal 100%. So that is how we calculate this 10%. Okay, and to answer the question back, what is the likely measurement error expressed as percentage of the output reading? So this is basically our output reading, 0.9 or 1.1, because we have a full scale error or full scale accuracy, whether it is a positive 1% or negative 1%. Or you can also, if you don't like to use this kind of calculation, you can also use this calculation as well. You just take the error, okay, the full scale reading inaccuracy or the full scale reading error, divide by your nominal value that you are measuring, okay, times 100, okay, and you will get your 10%. Okay, can you understand? There are several ways in order for you to calculate the percentage, but you need to think about what you're trying to calculate over here. And given that you know what is the full scale reading error, is it okay? All right, thank you, Jiaming.
Yes, doctor.
Easy, right? This one. All you need to do is you need to know the definition of this. What does it mean by full scale reading error? By using this error, you have several ways to calculate the percentage of the measurement error. All right, what does it mean by precision, repeatability, and also reproducibility? Okay, here it says precision is an instrument degree of freedom from random error, precise. High precision does not imply anything about measurement accuracy. Okay, this is weird. High precision does not imply anything about measurement accuracy. It's true, but maybe you have a question mark over there. How come precision is not the same as accuracy? Okay, later on I will show you what does it mean by difference between precision and also accuracy. All right, repeatability, the closeness of output reading when the same input is applied repeatability repeatedly over a short period of time, human condition, same instrument and observer, same location, same condition of maintained throughout. The keyword here is that closeness of output reading when same input is applied over and over again, repetitively. Considering that the measurement condition is the same throughout the time. On the other hand, reproducibility is the closeness of output reading when same input when there are changes in method of measurement. So it means that closeness of reading, um, we have a same input given to the system. However, method of measurement change. For example, the environment, the condition used, the time, and also the observer of the measuring instrument, the location as well. So that's the difference between repeatability and reproducibility. But normally, repeatability is more give us more information compared to reproducibility, because normally we don't try to measure a reading in different location or the different way to collect our reading. So normally we try to use the same method and also same environment to measure our items of our devices or our reading. Okay, this is what the difference between precision, repeatability, and also reproducibility. But I think based on the three pictures that you have over here, explain about precision and accuracy more, I think. Okay, look at the first one. If you look at the first one, the dot over here is scattered throughout this 1, 2, 3, 4 circle, inside this 4 circle. So you can see here that this one is this measuring or this robot is very low in precision and also low in accuracy. If you look at robot number 2, okay, our main idea is that we try to gather all dots in this middle circle. However, all dots available or appears in close to each other at the circle outside our target. So here it says that at this kind of measurement is high precision but low in accuracy. Precise but not accurate. Precise because it can give you the same answer, precise. But the accuracy is very low because our main target is to get values at the middle over here. And if you look at robot number 3, we have a high precision and also high accuracy because it reach our objective, that is to get together all dots inside this small circle at the middle, and also the circle, the dots is close to each other, means that when you try to do it all over again, it will give you the answer within the acceptable range that you required. So this is considered as high precision and high accuracy measurement. Okay, tolerance. What does it mean by tolerance? Tolerance here says closely related to accuracy and defines the maximum error that is to be expected in some value. Describe the maximum deviation of manufactured component from some specified value. Another way to describe about tolerance. But if you look the description that the thing that I mentioned earlier, recall back about full-scale error. It's more or less like this one. Okay, full-scale error tolerance. If you look at resistor, at the end of the resistor color lines, you have a color, whether it is gold, sometimes it is silver. So the lines over there describe about the tolerance of the resistor. I mean the tolerance of resistor value, whether it is 10% or 5% of the nominal value of the resistor. Okay, we have a look at the example. The example says here a packet of resistor bought in an electronic component shop give the nominal resistance value as 1 kilo ohm and the manufacturing tolerance as 5%. If one resistor is chosen at random from the packet, what is the minimum and maximum resistance value that this particular resistor is likely to have? So it's very easy. I think you just minus 5% from the nominal 1 kilo ohm will give you 950. This is the minimum value of the resistor due to this tolerance, and you plus 5% from the nominal value of your resistance will give you 1050 ohm or 1.05 kilo ohm for the maximum value of the resistor. So this example is basically try to address on how we can get minimum and also maximum value of our resistor in this case, given that the tolerance is 5%. So if you have a tolerance of 10%, so you need to calculate it again. And in details, how do we get this 950? Maybe 150 is quite straightforward. So we try to calculate based on this 5% value. So 5% of our nominal value, which is 1 kilo ohm, okay, when we equals to, we cancel these two. Okay, we have a 50 ohm value. So the first one is 1000 minus 50 ohm, which give us 950 ohm. The second one is 1000 plus 50 ohm, that will give us this 1050 ohm or 1.05 kilo ohm. Okay, any question? It's very easy, right? So far, I think the mathematics level is not that that hard. And believe me, throughout the course, the mathematics levels is manageable lah. It's not that hard for this course. Okay, I think this one I've explained earlier about the range or span. Sometimes we call it as range, sometimes we call it as span. The range here or span defines the minimum and maximum values of quantities that instrument is designed to measure. Okay, let's say based on example that we have earlier, we have 0 to 10 bar, right? Example that we calculate earlier, 0 to 10 bar. So the minimum here referring to this 0 value, and the maximum refer to this value. And maybe if you have multimeter, you can select your range of reading, 0 to 1 kilo ohm, maybe 0 to 10 kilo ohm, and the minimum is always 0, and the maximum depends on your selection. Maybe when we try to measure a bigger value of your resistor, you should put a selection which is higher than your expected value. Maybe when you try to measure a voltage, let's say outlet, 3-pin outlet at your house, you cannot put a range of your measuring instrument up until 10 volt because definitely it will destroy your instrument. Maybe you should change your ammeter or your multimeter selection to be in the mode of ammeter, and the range should be at least a bit higher than the expected value coming out from the 3-pin outlet. For example, in Malaysia, we have 240. I think that's its maximum value, maybe 220, 220 to 240. Maybe you can select your range of measuring instrument, for example, your multimeter up until 300. So you know that um, the value is slightly below that value. Is it okay so far?
Okay.
Okay,
Yes,
easy,
Doctor.
right?
Okay, Doctor.
All right. This is about linearity and non-linearity. Linearity means that a good fit straight line. Linear, right? Linear should it is uh, direct relationship, or in bahasa berkadar terus, I think linear um, in English, direct relationship between two quantities. So that doesn't mean that means by linear. So here linearity is a good fit straight line through series of measurement, and non-linearity means that defines the maximum deviation of any output reading marked x from the straight line. Non-linearity is usually expressed as percentage of full-scale reading. Maybe to make it easy to understand, if you have a straight line over here, relationship of your measurement, maybe this is measured quantity, MQ, this is output, your output reading. If you give, let's say, 1 ampere, this value also, okay, maybe it give you 2 volts, for example. And if you have 2 over here, 2 ampere maybe, this will give you 4 volts, your output reading. So if you put it in a graph or plot, it will no, okay, something like this lah. So it is linearly related base of our two quantities, measured quantity as well as our output from our instrument. The non-linearity means that if you give 1 over here, okay, let's say the first one, it will give you 2 volts over here. However, if you increase it to the measured quantity as 2, the measurement over here maybe 5, and for 3 maybe, let's say 3 over here. So look here, we have, okay, something like this lah. But we can always do approximate value, but approximate means that it's not that accuracy. So this is what I try to say here, is that the pattern of this graph, or maybe something like this later on, this is what we call as a non-linearity in our measurement. We don't know what to expect as we increase our measured quantity. Okay, sensitivity of measurement. This is important. Please remember this definition as well as the equation. Sensitivity of measurement meaning that measure of change in instrument output that occurs when quantity being measured changes by a given amount. In other words, I would like to say here is that if you have a series of measurement and you try to plot it like this, so the sensitivity means that the slope of this graph, okay, the slope of this graph is the sensitivity of your measurement. So here it says that the sensitivity of measurement is the slope of the straight line, i.e. the ratio of scale deflection and value of measurand reducing deflection. So the equation of sensitivity is scale deflection divided by value of measurand producing the deflection. Okay, maybe it's not that clear until we have a look at this example. Sorry for that. Okay, if you look at the example, the question here says that the following resistance value of a platinum resistant thermometer were measured at a range of temperature. Okay, resistance measured a range of temperature. Determine the measurement sensitivity of the instrument in ohms per degree Celsius. So how do we determine measurement sensitivity in this case? If you look at the solution, if these values are plotted on a graph, the straight line relationship between resistance change and temperature change is obvious. You see here, let's say I put it as, okay, here is the temperature, okay, maybe this is our resistance, or I cannot put it like this way, maybe I should label it as ohm, and this is degrees Celsius. We have 200, 230, 260, 90. And if you look at the difference between these four measurements, the first one we have 37. Maybe I put it as number 1 over here. Number 2 is 314. Pay attention at the difference over here. Difference is 7. Okay, means that the length over here should be the same. And from 314 to 221, also the difference is 7 as well. We can say that this is our, maybe I should put it as number, easy to understand. 37, 314, 321. And the last one is 328. Again, the difference is also 7. 7 over here. And if you look at the temperature as well, we have a difference of 30 degrees over here, 30 degrees, and 30 degrees. So we can say that the gap between this marking in our x-axis is also the same. So this is 200, 230, 260, 290. In other words, I would like to say that the gap over here is proportionate. So 30, 30, 30, and also 30. If you try to plot, okay, the first one and the second one and third one is over here, the fourth one up here. All right, then put a straight line here. You will see that there is a linearity of this measurement, and that's why it says that the straight line relationship between resistance and change, and temperature change is obvious. So for the solution, for the change in temperature of 30 degrees, the change in resistance is 7 ohm. You see that? 30 degrees over here, the change is 7 ohm. 30 degrees from here to here, also 7 ohm. Hence, the measurement sensitivity is, this is the scale deflection. Scale deflection over here is 7. And divided by the value of measurand producing the deflection. The deflection from one measurement to the other measurement also is 30 degrees. That's why here we have this answer, 0.233 ohm over degrees Celsius. Okay, there are two ways to use this formula. The first one, if you know it's exactly, you know exactly how to use it. The second one is by tips. If by is by looking at the units over here. You see here, units is ohm per Celsius, means that whatever at the top over here must be in the unit of ohm. And the value down here or at the denominator should the unit should be in degrees Celsius, means that this is the temperature. So that is how lah. If you know it, if you know exactly how to make the definition of scale deflection and also value of measure and producing deflection, then that should be okay. But I will give you a tips on how to identify what does it mean by scale deflection. Is it the temperature or is it the resistance? So looking at the required units over here, we need ohm per degree Celsius, meaning that at the top or the numerator over here should be the resistance value. Down here should be the temperature value. Okay. Are we clear?
Clear.
Okay.
Yes, Doctor.
Clear, Doctor.
Okay, next slide. It's about threshold. Thresholds mean a minimum level of input before the change in the instrument output reading is of a large enough magnitude to be detectable. Whew. It's difficult to understand from the definition itself. The second one is manufacturers vary in the way that they specify threshold for instrument quoted as absolute values of percentage of full scale reading. Okay, it makes our understanding more blur. To ease the meaning of threshold, have a look at the condition that we have down here. As an illustration, a car speedometer typically has a threshold of 15 kilometer per hour. Means that if the vehicle starts from rest and accelerate, no output reading is observed on the speedometer until the speed reach 15 kilometer per hour. So this is something which translate the meaning of threshold. Means that if you press something up until it's a certain value, the meter is not going to change. Until you pass that value, the threshold value, then it started to give value of the measurement or what you are doing. For example, this is pressing a vehicle throttle. All right. Sensitivity to disturbance. We have two factors over here. The first one is zero drift. The second one known as sensitivity drift. This is also very important. Maybe later on I will give you the example to on how to calculate zero drift as well as sensitivity drift. In general, okay, this disturbance is considered as a variation occurs in the ambient temperature, certain static instrument characteristic change, and the sensitivity to disturbance. Okay, and it is measured by its magnitude, the changes of its magnitude. So it is due to ambient, maybe some static characteristic change as well, and also disturbance, outside disturbance. All right. What does it mean by zero drift? Okay, zero drift sometimes called as bias. Okay, or maybe it's not that big enough. Okay. And describe the effect where zero reading of an instrument is modified by a change in ambient condition. So zero drift closely related to ambient condition and sometimes is called as bias. And it is it can be removed by calibration. And how do we calculate the drift magnitude? Here we have difference between the pair of output reading. Maybe at the moment you cannot see clearly what does it mean by difference between the pair of output reading. When we have a look at the example, maybe you will know, okay, this what it does it mean by zero drift. Zero drift coefficient, this is something which is also important, because typically for zero drift, it is given by its coefficient value. So to calculate zero drift coefficient value, we use this formula. We take the drift magnitude divided by the difference in temperature change. Why? Because typical unit of measured of this zero drift is measured by whether it's volts per Celsius, or sometimes maybe meter per Celsius, ohm per Celsius, but the denominator normally related to the temperature, because zero drift is closely related to the ambient condition, the change in ambient condition. And sensitivity drift, also known as a scale factor drift, here also varies as ambient condition change. So you expect that the sensitivity drift coefficient at the end, we have over Celsius over here, angular degree or bar per Celsius. So because it is related to ambient condition changes. All right, let's have a look at these three diagrams to explain about what does it mean by zero drift and also sensitivity drift. The one at your left over here, A, okay, we have a zero drift. See here, we have like a bias from our nominal characteristic. And if you look at the what do you call it, the slope or the gradient of this line is the same as the nominal characteristic line. The gradient is same for zero drift. However, if you look at for sensitivity drift, it started at the same point. However, the gradient or the slope of our line, our measurement is a bit different compared to the nominal characteristic line. So this is called as a sensitivity drift. And if you combine these two, we have both zero drift and sensitivity drift. Looking at this graph at the bottom of here, it is biased as well as the gradients is slightly changed. Okay, can anybody tells me which slope is higher, the nominal or the slope value is higher, the nominal or the one that the dotted line, or the without the dotted line over here? Which one have the higher value of slopes? Can someone respond to that?
I think the dotted line.
What, the dotted line is have a higher value of slope compared to the
line without dots.
without dots.
Without dots. Sorry.
Okay, without dots. Yeah, this is basic mathematics. Okay, is this slope is a positive slope or negative slope?
Positive.
Positive.
Positive. Thank you so much for your. Means that you know your basic lah. For negative slope means that the value the line should be from the y-axis towards the x-axis. Okay, this is considered a positive slope. Yeah. Okay. Example. The following table shows output measurement of voltmeter under two sets of condition. Okay, we have two sets of condition. The first one is measured voltage reading measured at 20 degrees per Celsius. The other one is voltage reading measured at the temperature of 50 degrees per Celsius. The definition or the condition that mentioned in the question, used in the environment and kept at 20 degrees Celsius, which is the temperature that was calibrated at, and used in environment at a temperature of 50 degrees Celsius. In other words, the condition, two conditions here says that this instrument is calibrated, or its nominal condition is at 20 degrees Celsius. So that's why if you look at the table here, we assume correct because this is the calibrated environment, or the instrument is calibrated at this 20 degrees Celsius. And we go to another environment and take the same instrument and try to make a reading. Another environment means that the temperature is a bit higher compared to the calibrated temperature. And this is the value of voltage reading of based on that the instrument gave. Okay, the question determine the zero drift when it is used in 50 degrees Celsius environment, assuming that the measurement value when it was used in 20 degrees Celsius environment are correct. Also calculate the zero drift coefficient. Okay, we have two questions over here. The first one is we need to find the zero drift magnitude. Okay, the second one we need to find zero drift coefficient. The first one is its zero drift value or zero drift magnitude. The second one is its coefficient. All right, zero drift, okay, can be found by using this solution. Here says that zero drift at the temperature of 50 degrees is the constant difference between the pairs of output reading. The pairs of output reading, that is 0.3 volts. Okay, how do we get that? You will see that this is the pair of output reading. Let's say this is pair number 1, this is pair number 2, this is pair number 3, and so on. Maybe I just write it over here. 8, not 5, 4. Okay, if you look at this pair, the difference is 0.3. How do you know it? 10.5 minus 10.2 is 0.3. And the second pair also gives us 0.3 value in terms of differences. The third pair also 0.3, and the fourth one is 0.3 as well. So it has a constant difference between pairs of output reading, and the value is 0.3 volts. And this 0.3 volt is basically referring to the zero drift magnitude, okay, or zero drift value. And for zero drift coefficient, okay, for zero drift coefficient, remember, for coefficient means that it will related to temperature, okay, temperature. And if you see the equation of zero drift coefficient at the denominator side, side, it says that the difference in temperature change. So this magnitude for okay, for the coefficient, we will take this 0.3 value or zero drift magnitude divided by the changes of temperature. See here, at first we have 20 degrees, and later on we try to make a measurement at 50 degrees. So the difference is 30 degrees Celsius. So that's why we got this answer. And we see here it's volts per degree Celsius. This is considered as volts because we know that the reading over here, the unit is volts. All units are volts over here. And the denominator side or the denominator value is the temperature. So this is basically 30 degrees. And that's why we have per degree Celsius over here. Right? Any questions so far?
So far, so good, Doctor.
Okay, yeah. But you need
I'm good,
to.
Doctor.
Okay, thank you so much. You need to what do you call it? To really have a look at the definition of what does it mean by zero drift? How and what does it mean by the coefficient? And the equation to get the answer is very easy. Right? Another example, we have a spring balance is calibrated in an environment at temperature of 20 degrees and has the following deflection or load characteristic. Okay, we have deflection over here, and we have a load of 0 to 3 kilogram. It is then used in environment at temperature of 30 degrees Celsius, and the following deflection or load characteristic is measured by this value. The first question is try to find what is zero drift, and second, sensitive drift. Sensitive drift per degree Celsius. Okay, change in temperature. Okay, this is quite tricky. Actually, this part try to make us confused. Am I looking at zero drift only or zero drift coefficient? Same goes to sensitivity drift. Am I looking at sensitive drift or sensitive drift coefficient? Actually, based on the solution over here, you need to calculate both zero drift and zero drift coefficient because it's given here that per degree Celsius, zero drift per degree Celsius means that you need to calculate the zero drift as well as the coefficient as well. And also, looking at the sensitivity drift per degree Celsius. Again, sensitivity drift means that we try to find the slope of our measurement, and to find the coefficient of the slope or sensitivity drift, you need to add per degree Celsius over here. Okay, looking at the solution. At 20 degrees Celsius, deflection load characteristic is a straight line. Sensitivity is 20 millimeter per kilogram. How do this 20 millimeter per kilogram come across? Basically, if you look at here, and when you try to plot it in, maybe this is kilogram. This is your deflection in millimeter. Okay, 0, 1, 2, 3. And the value here is 0, 20, 40, 60. And the, not here. Okay. Another one is here. Maybe I should label it as 1, 2, 3. This is 20, 40, and 60. 0 and 0. You have a straight line over here, and the sensitivity is the slope of this graph. So how do you find the slope of this graph? Changes over here, okay, changes over here divided by changes at your x-axis, or the gradient m. Gradient. Do you understand what is m? You always come across with symbol of m for gradient?
Yes.
Okay, maybe m here is equals to 40. Let's say I take 40 minus 20. I take 2 points, this point and this point, divided by 2 minus 1, and that gives me 20 millimeter per kilogram. So sensitivity is related to gradient. Or slope. Okay. For 30 degrees Celsius, you apply the same strategy and you find that the sensitivity is 22 millimeter per kg. Okay, we're done with the value of the sensitivity at 20 and 30 degrees. For zero drift or bias, okay, the first one is 5 millimeter. How do we get this 5 millimeter? You see here, at zero, at no load deflection, we have 5 millimeter over here. Changes in at 0 point. So this is considered as our zero drift magnitude. And okay, since this is combination of zero and sensitivity drift, so you might find that the slope or the value over here is not changed according to what we have at the zero level. In other words, I would say maybe you would think about this 20, this one should be a 25, this 40, this should be a 40, 45 maybe, 60, maybe this should be a 65. So it's not like that, because this is combination between zero drift and sensitivity drift. If you look at our earlier, okay, here, okay, this is what it looks like basically. It's not looks like this because this is considered only a zero drift. We only exists a zero drift. This is sensitivity drift. When we combine, it should gives us this kind of graph. So you don't expect that no, here the value over here 20 become 25, 40 become 45. It's not gonna work like that because the slope had changed a bit due to the sensitivity drift. So what you can refer is that you can refer the no load deflection at the origin. So here we have 0 and 5. So the deflection over here, the difference is 5 millimeter. And now to calculate the zero drift, just add the temperature difference in your calculation. The temperature difference here, C, is the change between 30 degrees minus 20 degrees, okay, which is 10 degrees. So that's why you have 5 divided by 10, and at the end you will get 0.5 millimeter per Celsius. And for sensitivity drift, why you have 2 millimeter per kg? Okay, because this is the difference between 22 minus 20. Okay, we have two readings over here, two sensitivity readings. We have one at 30 degrees Celsius, another one at 20 degrees Celsius. So the changes between the temperature is 2 millimeter per kilogram. So that's why to calculate the coefficient, basically this is coefficient, you need to divide this one with 10 degrees Celsius, and it gives you this 0.2 millimeter per kilogram per degree Celsius. Okay? Is it understood? Is it okay? Is it okay at the moment?
Okay, Doctor.
All right. This,
It's okay, Doctor.
this might be confusing for some of you guys because you might wondering how this value come across, come across based on what I've known earlier. Is it the correct way to calculate it? Maybe you have all those questions in your mind, but here I explain. Hopefully you can get my explanation well. All right, we move on to maybe our last bit of this lecture. It's about hysteresis effect. I'm not gonna get into details on this one because I think I put one question in your homework about hysteresis effect. But what I can tell you is that this hysteresis effect normally appears in equipment. For example, we have a ferromagnetic materials in our instrument. For example, if we have transformers, of course, we have a core of the transformer is made by ferromagnetic materials. And basically, due to that, the ferromagnetic material itself have a what do you call it? Specific characteristic of that material. Maybe iron have different characteristic compared to cast iron, for example, pure iron and cast iron. So the hysteresis effect of the material itself a bit differ, and this is what happened when we have hysteresis effect in our measurement instrument or in our equipment. So this is known as loading and unloading curve or hysteresis curve. Okay, I'm not gonna get into details on this. I need you guys to read about it. I prepare a video for you to understand about the hysteresis effect. Okay, if you maybe I try to give a brief idea lah, because this is something very new. If you look at a solenoid, solenoid wounded by a coil, what happens if you inject current to that coil? What happened actually? For example, like this, if you have this is solenoid and you wound a coil over here and I inject current over here, what happened actually to this thing, to this setup? Anybody know? Formation of magnetic field. Yeah, correct. Okay, this hysteresis effect is closely related to what you are mentioned over here, formation of magnetic field. This is the loading and unloading effect. For example, if you try to increase the current over here. Yeah? We try increase. Let's say this is the field strength. Okay, field strength. This is your flux density or Tesla. If you increase the current over here, what happened to this material? It will develop a magnetic field density up until it's saturated over here. And if you decrease the current, it will not get into the same route as it grows, it's developed its Tesla or develop its field strength and also field density. We would expect that this is if we increase the current, okay, the density increase like this as well as the strength. But we cannot expect that if we put out the current, decrease the current, we're going back to this line back. Okay, what happened is it will follow the envelope over here. Okay, as we decrease the current until 0, and you see here we have, okay, additional value of flux density, although without any current applied. So the magnetic field strength is 0 since we don't have any current applied, but we do have the flux density over here. And as we push the current towards the opposite direction or give a negative current, okay, and the field density and also the field strength will follow this envelope over here up until it's saturated at certain point, the maximum value of our negative current. And of course, as happened at the beginning, we cannot expect that if we change the polarity of a current and it will follow the same route. Okay? If we here we have a very negative current, okay, let's say here is a very high or not very high lah, it's up until saturates value of current. We cannot expect that the pattern of magnetic field density and also strength will follow back what we have over here. It will go around this envelope and up until this point. I'll say, first this point when the current is 0, and if we try to push back into a positive value of current, and it will follow this route and up until its highest value of positive current and saturates over here. So this is the envelope of hysteresis fluid. So the size of this envelope might differ for different material. For example, material which is soft material, the what you call it, the envelope size is a bit thinner compared to a hard material where we have a bigger area. Okay, that's which is something different from what we have over here. But the one that I explained to you, it's actually inside the video that I put it in your e-learning portal. Okay, what is the significance of this hysteresis effect? Okay, now this is something which is items that related to hysteresis effect, but later on I will explain what is the significance of this hysteresis effect. Okay, hysteresis effect might happen in maybe magnetic material. For example, we have solenoid over there. Earlier I explained about that, and also maybe it happened in equipment which involves springs. Okay, also would contribute hysteresis effect as well. Okay, this is what I'm going to tell you about the significance of hysteresis effect. So here, if you look at this hysteresis envelope, it will introduce some area known as dead space. Okay, known as dead space. The space where people die. Dead space, not people die. Dead space. Defined as the range of different values over which there is no change in output values. Okay. This is to threshold definition that we looked earlier, but this is known as dead space. Normally, happen in gearing system, maybe in bolt and nuts system, something like that. So dead space is very some call it if you involved with a project or involved with high machinery equipment, this we try to reduce the effect of this dead space, and the dead space is due to hysteresis problem and also the backlash problem. Backlash is normally caused by normally happen in gear set of our machinery. So dead space of backlash normally it is dead space presented by this graph, and also dead space in hysteresis is presented by this graph. So this is very crucial, basically, the problem that we are facing over here, because you see here if we increase the value of measured variable, we cannot see any output reading over here. Okay, until we reach certain point, then we can see, oh, okay, the output reading is developing, whether it's increasing or decreasing. Decreasing means that at the negative side. So this area is very crucial. Okay. Application normally based on my experience, yeah, maybe you have other experience. Because my research is dealing with autonomous vehicle, this backlash or this dead space problem is very crucial, because we try to give the correct value of our steering angle, of our throttle position, something like that. If we have this dead space, we don't know what is the output or what is the angle of our steering at the moment, and also we don't know what is the throttle position of our vehicle at the moment. Then our control system or our processing system of of our autonomous structure will become haywire. So that is, I think, crucial issue to be tackled. So that's a way to not eliminate, just decrease the effect of this backlash as well as this hysteresis. Maybe in transformer, for hysteresis, the way you reduce it is by make the iron core in a laminated manner. I mean laminated structure. So you don't use a bulk iron core. You split it into laminated pieces. For backlash, maybe you can add anti-backlash gear in your gearing system, or you try to fix the setup of your gear sets in order to reduce the backlash effect. So that's the importance for this dead space situation or dead space issue. All right. The last one is exercise. I believe this exercise you can also find in your homework. And I think that's all for this week. Okay. You have any questions so far?
No, doctor.
Is it clear? Everything is clear?
Yes, doctor.
Okay.